So in this chapter, I'm going to talk about how to compute the sum of reciprocal Fibonacci sequences. So, most time when we talk about learning math and be perfect in lots of problem solving skills, we talk about practice makes perfect. But in this type of problem, you can definitely see if you only practice like simple problems, you won't be able to come up with an idea to solve this type of Fibonacci sums, which actually requires very advanced knowledge of mathematics. I'm not going to show all the proofs here, but I will just use the result from this paper, and we'll go through some of the background and helps to understand why we cannot use simple expression to describe this sum. And before we start, I'm kind of busy this week with the joint math meeting 2026 in Washington D.C. I'm still on trip. I just can share you some photos I took in the conference. It is quite advanced event with many interesting talks and poster sessions, and people post their mathematical arts and research. And this field medalist June was also there giving a talk. And overall weather is really nice as the conference proceeds. And you can see this is the exhibitors session. We have a lot of publishers and the students doing posters share their undergraduate research. So overall, it's a great event. And if anyone interested in mathematics, you should come to this event. And we also have like advanced topics on recent breakthrough on Kakeya conjecture by Hickman. He reviewed the connection about Kakeya conjectures and the harmonic analysis, which is kind of new for me. It's more or less like a topic to like popular science cover the history and toward the general publics. So this is something I feel like it's unique, very unique in JMM. So you have the greatest mathematicians to talk to, people not familiar with the field with deep, very, very in-depth knowledge and very smooth lectures. So this I learned quite much from that one. Again, there's some pictures from the students doing poster session. There are two, one in the morning and one in the afternoon. And I am very surprised that a lot of the research covers applied and pure mathematics in quite much depth, including modular forms, complex analysis stuff. So that's quite impressive. And I also kind of like these mathematical art part. So they show some 3D prints or posters, usually with nice topology and computer aided design. So it's definitely something you should check in the conference. And this is the entrance of the exhibitor hall. Some repeating, and this is a sort of what the poster looks like if you take larger picture and zoom in. And the publisher's book, some of the lectures on graph theories. This one's about friendship graph and neighborhood bicoloring graph, I think. Yeah, I still need to read some of the papers and the review, short videos I take on the lectures. Okay, this is also from undergrad research paper for graph coloring and integer sequence. This is very interesting. This is in front of a restaurant in Georgetown. And this is a lecture about pattern avoiding permutations. So there are still like lots of things I need to go over. I usually only go to algebraic geometry, complex analysis, and this probability really or combinatorial related talks. But otherwise, and maybe graphs a little bit. For other realm, I think it's just too advanced or something I really out of my reach. Okay, So this is it, and hopefully see you guys next year in Chicago. Okay, let's go back to this topics on Fibonacci sequence. Fibonacci sequence are very well known, so I will just skip the definition. You know, it's starting from 0, 1, and the next term is the sum of two previous one. Sometimes we start with the 1, 1 or 0, 1, so it depends on your convention. For a Fibonacci sequence, it has a really nice, I call the absorption properties. Say if you want to sum up k terms, it's from 1 to n terms for k from 1 to n. You really don't have to compute the sum one by one, because this absorption property tells you that the sum looks like a part of the sequence. So this is quite common for a power series or geometric series. Say if you have sum 2 to the power of n for k from 1 to n, it also has something like this. You have 2 to the power n, and it looks like some term in the sequence itself. And usually, if we know the form of the sum, we can also quickly check the exponential, the growth rate for Fibonacci number if we want. So in this case, you can tell that because this guy looks like part of the terms, so the sum and each term actually grows in a very similar manner. This is can be interpreted by this very simple example for 2 to the power n, because for exponentials, say if you have lots of algae, it takes 40 days to cover the entire pond. So how long does it take to cover only half of it? So it's 39 days. So for fast growing, like exponential growing sequence, every next step is more than everything you add up until the previous term in the sequence. Therefore, the growth rate of the Fibonacci, each term should look exactly like the growth rate of its sum. This can be easily intuitively understood with this type of argument. And for some of the variations, say if you have sum of Fibonacci k to the power 2 or squared, then you can tell this is also a term that really makes sense, because if you know Binet formula for that, it's alpha. The alpha it's like this. It's alpha to the power of n minus beta to the power of n, and divide alpha minus 2. But usually alpha is greater than 1, beta is less than 1. So for this guy, so each term should looks like alpha to the power of 2n. And for this term, it is true, because as we say, for the sum of the prefix sums, which means from 1 to n, the sum should look like a term, like in the sequence, maybe 1 next to n, or maybe 2 terms after n. And in this case, this looks same. This is also something look like alpha to the power of 2n in this formula. So you can tell definitely this absorption property also works for Fibonacci to the power of 2. So in general, you can tell that because of the Binet formula, if you sum up Fibonacci number to the power of n, or more generic p, let's call it, because n is like duplicate here. So p. So you should have something look like this, with the p terms multiplied together, and that will actually make it something close to alpha to the 2 times alpha to the power of the p times n. So if you check with the limit, say Fibonacci n times Fibonacci n plus 1, and it's over the golden ratio, power over 2, and it should be constant, and which means they are asymptotically the same. This is part of the Binet formula. That's the sort of alpha part in this formula, and the beta is usually a 1 minus alpha. Okay, and we can also take a look at the growth rate of Fibonacci k square. It should look very similar to Fibonacci k on logarithm scale. The only difference is the slope is probably changed, but they all should look like linear increasing on logarithm scale, because eventually it's log alpha to the power of something, and it's n times log alpha, right, for the simplified expression, and the n times something means it's linear in the log space. And another useful formula that we use is in this to basically solve this type problem is we can take a look at the prefix sum of Fibonacci number at even and odd index. So for this example, if you have Fibonacci number chosen at 1, 3, 5, 7, and so on, you have this sequence. It's only we pick up the prefix sum using only odd terms, and then you can just find this formula for this guy and using a function that's available in the result function repository. It shows you the definition of these functions on the page. And usually on OEIS it comes with this type of formula for you if this is like well known. So this is definitely linear recurrence. It satisfied an equal to 3 times an minus 1 minus an minus 2. So in this expression, you can see this is like first term, second term, third term. Okay, even though it is only odd for Fibonacci, but for n you have to take a number from 1, 2, 3, 4, 5, 6, 7, and so on. So this is something you want to be careful. And this is a term that you can check with the Fibonacci numbers. And if you look at these odd terms and even terms, so the sum of all the terms is exactly the Fibonacci 2n, just like what it says here, right? And we can do the same thing for n only choosing even terms. We solve that and use the same functions that connects to the OEIS and check if we have that. And we do have a couple of them, but if you take a look at these guys, they are almost the same, but the only difference is the leading terms. So we can use this guy. It says the an equal to Fibonacci times 2n plus 1 minus 1. So we do the same thing for these terms. It's 1, 4, 12, 33, 88, 232. So 1, 4, 12, 33, 88, 230. So it's the same, which also shows even you add the terms with the same parity, which means you only pick all the terms or even terms, the absorption property also applies. So the sum of even terms is the sort of all the term, one sum all the term minus 1. So you still don't have to compute everything by yourself and just apply the absorption properties. But the things get really tricky if you want to handle the inverse. So say, if you have learned continuity, analytic continuity, you want to apply a very simple extension based on the properties of the sum of Fibonacci. So I often show you the Fibonacci formula, the sum of Fibonacci formula with if the power is 2 or it's just itself. So can you do it with by simply change the power to -1? Well, technically you can do it. For example, the sum of 1 over Fibonacci, it gives you such complicated result. It composed of elliptic theta, Q analogs, and golden ratios, and it's wrapped, outside inside a parenthesis, and you times arc. It's arc the inverse of some hyperbolic tricks. It's really complicated. If we do the same thing for the terms with only even indices, this is that, and I think this part should be improved in the future. So it should be the guy above minus something in the bottom. Okay, but even the numerical value or the symbolic value gives you some important like symbolic expression for that, but it's still very hard for us to understand how you actually get this thing, and what's its connection to this elliptic theta. Probably very few people have heard of this if you just study sort of elementary math or even just calculus. This is definitely something requires you understand the genius work by Jacob, Jacob, back in I think 18th or 17th century. They study extensively about elliptic integral, which comes from computing the circumference of ellipse, which is really difficult, and I don't think we have we should just show the whole theory in this chapter. But there's a paper online that shows you how to do this type of thing. It's called Elliptic Functions in the Lambert series. It's published on Fibonacci Quarterly, so you can search that. And because this paper is quite old, so it's free for you guys to download from that webpage. So of course we can just use built-in functions to directly compute this sum. Okay, but how it's connected to the formulas inside this page, I will just give you a quick recap of how to do this after the backgrounds we have so far. So the author is Horadam, and the name of the paper in complete form is Elliptic Functions and Lambert Series in Summation of Reciprocals in Certain Recurrence Generated Sequences. So this is not limited to Fibonacci sequence. It's quite a generic method to compute anything. I think it's satisfy this type of two-term linear recurrence. So let's take a look at the functions that we can use. So what is the first thing we need here is elliptic k. It's the same thing as this guy, but the only difference is it depends on a parameter called k. But in here it's k squared, but in Wolfram the 103 is k squared. So the parameter they call as m is k squared. It's probably from different conventions, and we can verify that these two things are the same. So k here, I assume it means complete. Why it's complete? It's a 0 to pi over 2. So if you want to do something other than pi over 2, it's elliptic e. It's an incomplete integral. And let's check those two are the same. It's elliptic k. You plug 1.3 or 1 over 3 in the form, and I put a dot here to make the floating number. Otherwise, it will hold. And for integration, it's 1 over this guy. So 1 over this guy, and then just remember we use 1 over 3 as a k squared instead of k. So these should be the same. Okay, and these two are the sort of the formula that's used to be underneath this elliptic theta. Okay, and the next step is we should check using the formula that used in this paper that's actually related to these two functions. So let's go to the paper. It says if you want to compute these elliptic expansion, which is actually used here for omega 2n minus 1. And this omega can be replaced with Fibonacci or Pell sequence that used in this paper. So how do we use this formula? Is you can see it's either you computed R, you need to figure out what its R is, or figure out what is the K or the capital K is. Okay, because you can tell that K and the capital K are dependent. So you plug a K and you have another K here, right? And then you have K prime here, you have K prime here. And if you have K squared plus K prime squared equal to 1, these two things are called so related, and the K prime is sort of like cosine and sine relation. It's the complement of K. And if you have R in this expression, and we can definitely solve for this K. So basically, everything is connected. It's a function that you need to know the lowercase k and solve for larger K, and you have R, and K, R satisfy this equation, and that's the formula that we need to use for this guy. And how do you solve for this K-R relation? And it also shows that's why there's really no easy closed form for that. And so even for so you can see there's symbolic form, but this is really not that close, because this thing, if you want to compute it, you have to use a series of that. Okay, even though it's a name for a really complicated thing. It's not something like you only have a square root of 2 or a square root of 3 in your equation. So to solve this equation, we basically need to find the proper R or K in this case to solve this one. So this is the S1. It's the type of a formula that's we used here. So you can just plug in 1 over 3 times pi over 2. It will definitely gives you the elliptic integral. It's the same value here. And this is corresponded to the formula 2. So the S2 is 2 times kk over pi equal to this guy. So if you want to compute k, so you basically compute lots of terms on the right-hand side times pi and divide it to k. So this is also the formula that's give you the same result at capital K. So you can see 1.73392, same thing here, same thing here, same thing here. So this checks this formula as the same thing as the two Wolfram language code used here. Okay, and also we can just visualize if we want to specify value and how it's intersect with a curve. So this is a sort of a simple visualization of how this value and the curve, basically looking for inverse function to find the value of x given any value of y. Okay, the next step is how to find the proper R that used for this computation. It is the solution. The cell is a variable that stores this guy. So what it does is actually it solves implicitly. What you need to do is in this case here R should be beta square. So you need an expression to find m in terms of beta, and R is the known. NOME. It's e to the power of minus k prime over p times pi over k. This is uppercase k, which means it is elliptic. So here we used exactly the same thing expression here. It's exp times minus 1 minus m, because you recall this is the complement relationship between the two expressions. So 1 minus m times pi over elliptic k, and take the minus and do the exponential. It is equal to square root of 5 minus 1 over 2 to the square. And I just give the guess, I just randomly put an initial guess for that, because this function looks quite smooth. So the convergence should be really good if you just give it a reasonable number between 0 and 1. So, and it just put a lot of precisions to that, so I can check the result and the brute force result above. So you solve that, and this is the m that we want to find. So this is m is the value is 0.9943 61 or something like that, right? And then if to use the formula to find the inverse sum in the numerical value, all you need to do is just plug this solution back into this formula. So this is this is a solution m, and the k is the square root of m. So you need a square root of and this is elliptic so this guy, and over 2 pi to give you the result. Let's compare that to this guy, and we can put precision at 52 here. Yep, so they are very identical to the last one. It's from the uncertainty accumulated from the numerical computation here. So if you take a look, the final precision of this guy is only 50 digits. So we can just remove 2 with replace with 0, and they will look like exactly the same. Okay, so that's it. If you want to compute other terms simply using the same formula and solve for k, this will be definitely a different k, because, well, even though this formula looks the same, but make sure that you check the actual value of the r is based on the beta square, and beta is from you solving the recurrence formula for this something Fibonacci type of sequence. So you can tell usually it's formed like something like this. And for different initial condition, the alpha beta will change, and once it changes, it simply change the part here, and it will give you definitely a different m. And of course, if you go back to the formula, the square root of 2 will be replaced. The square root of 5 will be replaced by the square root of 2. So eventually, you have the same workflow that can basically solve all the problems in this paper with this same routine. All right, thanks for listening, and hopefully I see some of the guys in the JMM in 2027 in Chicago. Bye bye.